Hey guys, today we'll talk about chapter 3.8, derivatives of inverse functions and logarithms. So let me first introduce you inverse functions. Again, you have learned it from chapter, I think 1. It was in chapter 1. But let's quickly review it. So what is fx? What is inverse of fx? So let's say we have set of A and set of B. And of course we have x's here, we have y's here. So we have a function f, and it maps elements from set A to set B. But in inverse function, it will be vice versa. So inverse of fx, of course, denoted as like this, and will map elements from set B back to set A. So it won't be not in the direction. Let's say this is fx, but in inverse of fx, it will go like this. It will map from B to the A. And like to find inverse function, we have to find in easy way. We have to find x in the function and then change roles to put y instead of x and put y instead of x instead of y. Let's say, for example, we have fx equals to 2x minus 5. It means y equals to 2x minus 5, and we're supposed to find inverse of fx. So we'll just find x in this function. 2x equals to y plus 5, x equals to y plus 5 over 2. And then we will just change x and y. Y equals to x plus 5 over 2. It means inverse function, our inverse function will be x plus 5 over 2. And that's it. And what you have to know about inverse functions is they have to, like, original function must be one-to-one injective. What does that mean, one-to-one? It means that each element in the domain maps to a unique element. So we cannot have, let's say, 2 or 3 elements which maps just for one x. We cannot have 2 y's. Basically, it means that. And the one thing also is important about inverse function is graph. So you have to remember just one key point here, and it's important. So when you graph fx and inverse function of that function, you have to remember that their graphs will be reflection of each other across the line y equals x. And let's show it here. Oops. But they will pass from the origin, and this is y equals x. And also, I think in your book also, yes, there is y equals 2x minus 2. This is original function here, yellow line, and reflection on it. You can see the y equals x red line, an inverse function. Okay, I think that's it about inverse functions, and let's see what about derivatives. So we know that how to find derivative of function. What about derivative of inverse function? Let's say we have this function. So how can we find? We can find derivative of fx. We know that it will be 2. But what about derivatives of inverse function? Let's see the book, what we have here. We have fx equals 1 over 2x plus 1. And derivative of it is 2x minus 2. And of course, it's easy to find derivative of both. We know how to find it using sum rules. Yeah, using sum rule. Okay, but this is not a special case. What does that mean? It means, let's say we don't know what is a function. Let's say we have complex functions, and to find derivative of inverse of that function, we have to first find inverse and then to find derivative, but it will take time, a lot of time. To solve that problem, we have a formula, rule, or you can say it as rule. So we know that, let's say fx, not fx, but let's write it like this. fa equals to b. Yes. And f inverse of f, b equals to a. It's obvious, of course, because domain of main function is range of inverse function. We knew that. Now, and also it is obvious that fa equals to 1 over f, like inverse function. For example, if we have to find the inverse function of 5, we know that it's 1 over inverse of 5, it's 1 over 5. And using derivative, we can write it as, like you can see from the book, f derivative b equals to 1 over f derivative a. Yes. And what is a? A is range of inverse function. You can see it like from this. So it means we can write, instead of a, f inverse b. So f derivative f inverse b. So we found that f inverse b equals to 1 over f derivative of course, derivative of inverse function equals to f derivative f inverse b. Yeah, let's see some examples, and you should remember this, by the way. I mean, it's easy. You can find it writing as, let's say you don't, you forgot it in your exams, you don't know like what is derivative of inverse function. You can write all this and you will get at the end this formula. Let's see what we have here. Okay, to prove it, it's theorem, by the way. Let's see what is in here. So we know that f inverse x equals to x. Yes. Of course, when you can show it and you can prove it, it's obvious, because if we put here instead of a f inverse b, you will get b. You have to get b. And yes, let's take derivative of both sides. D over dx f inverse x equals to derivative of x, and it's 1, obviously. And to find derivative of left function, of course we write derivative of f inverse x, and of course we know that from the chain rule we have to take derivative of inside function. So f, also we have to consider d over dx f inverse x. And also from the previous chapter, it was about implicit differentiation. We know that we have to find d over dx. And d over dx f inverse x. And what does that mean? It means d over dx. So we know dy over dx means y prime. So we can write, instead of y, any function. d2x over dx means derivative of 2x. And d over dx f inverse function means derivative of inverse function. Please never confuse. When you see d over dx f inverse x, don't say that, oh my god, what is it? It's derivative, nothing else. And it equals to 1 over f derivative f inverse x. It's easy to prove it, just few lines. Let's see the example. So we have function x squared. X will take the positive side. Of course, we know that if we take both sides of x squared, we won't have inverse. That's why we have to take positive side, either positive side or negative side. Inverse of x squared is square root of x, and derivative of fx is 2x. Derivative of inverse function is, we know, 1 over 2 square root of x. And here they just wanted to prove it using our formula, like this formula. Let's write it using this formula. Okay, so we have fx equals to x squared, and of course x greater than equal to 0, and inverse function is square root of x. And let's say we have to find derivative of inverse function equals to, we'll write formula 1 over f derivative f inverse x. Yes. And then one over f derivative square root of x. Why? Because f inverse x is square root of x. We'll just plug in here. So we have to find f derivative square root of x. So what is f derivative x? Derivative of main function 2x. What is derivative of square root of x? We will just put, instead of x, square root of x. Never ever find square root of x in this case. Never write derivative of this equals to derivative of square root of x. No, it's not your function, it is just x. Never. Okay, we'll just put in we found that f derivative square root of x equals to 2 square root of x. So the answer is this. See, it's easy. Okay, next. Derivative of natural logarithm function. Let's first solve few questions about inverse function, then let's go to natural logarithm functions. Of course, it's e. We know that. And yeah. Okay. We have exercises. I think derivative of logarithmic differentiation. Okay, this all about logarithm. Yeah, it's a nice chapter, by the way. Derivative of inverse function. Let me solve few questions from 1 to 4 or 1 to 10. 1 to 10. Let me choose, I don't know. 4 is easy. Let's take 2. Chapter 3.8, question 2. Okay, we have fx equals to 1 over 5x plus 7. And we have a equals to minus 1. Let's read the condition. Okay, we have 3 subtasks. In A, we have to find inverse of fx. Okay, let's find it. Equals to question mark. So fx equals to 1 over 5x plus 7. We have to find x. 1 over 5x equals to, let's write it like, okay, fx. Fx minus 7. X equals to 5. Fx minus 35. Not equals, minus 35. Okay, and let's change the roles. Equals to 5x minus 35 inverse. Yeah, let's not put inverse in here. Wait a second. Okay. Minus 1. Here's our inverse function. Nice. We found it. Down. Let's see B. Graph f and f inverse together. Okay, let's try. You can use GeoGebra. Or there are easy functions. Let's try to draw it. Okay. So, you can draw how to draw function. You can create tables first for fx. What was fx? 1 over 5x plus 7. Okay, let's create table for fx. X is here, y here. Let's say you don't know how to find. You can see obviously here k is positive. If it's positive, it means your graph, the alpha will be positive. Your lines will be either like this, because if k is positive, this angle here should be less than 90 degree. But if k is negative number, then angle will be greater than 90 degree. It will be like this. Remember this. Okay, but let's say when you have complex functions, please create table x and y, and then put 0, 1, 2, -1, -2, and then find y's, and then just put in x like in coordinate system. But here, I mean, this is kx plus 1b. It's easy to draw, no need to waste time. But remember, when you have again complex functions and you're supposed to draw them in your quizzes, final or midterm exams, use just table. I mean, what else you have to do? Okay, we know that when x is 0, y is 7, and when y is 0, x is -7/5, and k is 1/5. Okay, I mean, we know a lot of information. Let's draw function here. Not here, but let me draw it here. Okay. By the way, if you want, please let me know. Like, if you want this document, I can share it as PDF. Okay, when this is x-axis, this is y-axis. When x is 0, y is 7. Let's take it here, 7. And when y is 0, x is -7/5. Okay, that's nice. And then graph will be like this, and k is positive. That's why, oh my god, it's terrible. Yeah, somehow. Okay, so this is fx. And now let's draw. I don't think this line will be like parallel to y equals -x, but let me draw it in a different way, because it seems like they're parallel, but they're not. I mean, it's not possible. Let's draw it first. I think it will be something like this. This is I think, okay, still parallel, but anyways, they're not parallel. No, 7/5 -7/5. Okay, this is fx. And now let's draw inverse function. X, we found it that 5x - 35. When x is 0, f inverse x equals to -35. Okay, and when y is 0, x is y, I mean, the inverse function is 0, x is 7, yes, and the k is 5 greater than 0, then it means our angle will be less than 90 degrees. Okay, so let me draw it with different color, green and red. So when x is 0, function is Okay, 35. Let me take it here. Minus 35. No, it's not possible to take. It's ridiculous, actually. Let's make it. I'll make it our y-axis a little bit longer. Now, yes, minus 35. And when y is 0, x is 7. Okay, 7. And then function will be something like this. Okay, somehow. It looks ugly, but actually, if you draw it in GeoGebra, they should intersect actually. But our line is like this function is not drawn correctly by me. I want you to see that intersection point. That's why I'm doing this. By the way, you can ask, how do you know that they will intersect? Good question. What was our function? Plus 7. To find the intersection point, you have to equalize function and inverse function. Mm. 7 plus 35 equals to 5x plus 1 over, no, not plus, minus. 40 equals to 24x over 5. X equals to, so you have x, you have point, that's why I know that they will intersect. You have coordinate, you have x, and you will just put it in here or here, doesn't matter, and you will find y, and it will be your intersection point. Yeah. Okay, it will be something like this, I guess. It's a little bit ugly, but sorry about that. And then they will intersect at some point here. Something like this. You use GeoGebra, please. Ignore this ugly picture, ugly graph in here. Okay. This is 7. Anyways. C. Evaluate df over dx at x equal a. Okay. We have to find derivative of fx and x equal a, and also inverse function. Inverse derivative at, again, x equal, of course, fa, and show that at these points derivative of inverse function is equal to 1 over derivative of main function. So we have to show that df inverse over dx equals to 1 over df over dx. Oh, no parentheses here. Okay, that's nice. Let's find derivative of first. Fx. df over dx equals to, so our function was no need, okay, 1 over 5x plus 7 inverse derivative, sorry. Okay, we know that we can use sum rule. Plus derivative of 7 equals to 1 over 5, and this is 0. Okay, and never forget that a is equal to minus 1 in our case. And second, this is this color. We have to find derivative of inverse function f inverse x. Df inverse over dx equals to, we found our inverse function 5x minus 35. Inverse derivative equals to derivative of 5x minus derivative of 35 equals to 5, and I mean we can see that 1 over 5 is equal to 1 over 5, or vice versa. We have to show that df inverse this. So what is derivative of inverse function is 5 really equals to 1 over df over dx. 1 over 5 equals to 5. Proved. Okay, and that's it, I think. Yeah. But using our formula, how can we find derivative of inverse function? So our formula equals to derivative 1 over f derivative f inverse x. Yes, let's use this f derivative. What was derivative of inverse of function, our function 5x minus 35? Yes, and we found derivative of main function. It was 1 over 5, and remember it's constant function. Yes, derivative of our main function is constant, 1 over 5. There's no x in here, so it means doesn't matter what you put instead of x, you will get 1 over 5 at the end of the day. So it doesn't matter what you have in here, derivative will be 1 over 5. 1 over 1 over 5 equals to 5. Really? Yes. See, they're equal. So you can use your formula, or you can use you can find derivative of inverse function in this way. It doesn't matter. Just remember this formula. But these are easy functions. But when you have complicated functions, you will see that it's used much easier using this formula than this way. Okay, we will solve these problems probably on Sunday, but I just want you to show some examples. Okay, let's see derivatives of logarithms. I don't want to keep this video long, because it can be boring, but also it can be difficult for me to download it, like upload it to YouTube for you. It will take time, a lot of time. Okay, let's see inverse of derivative of, not inverse, derivative of natural logarithm function. I think you understand derivative of inverse function. Again, you have to remember just one thing about derivative of inverse function. And that is this formula. It's easy to remember, I think, and easy to apply. derivative f inverse x. Oops. And that's it. Okay, now let's move on to the next part, derivative of the natural logarithm function. Why it is related to inverse function? I mean, why you cover this topic after the inverse function, derivative of inverse functions? Because we know that if we take fx as e to the power of x, inverse of fx is 1 over e to the power of x, and this is ln x. And actually it's not that much correct to write it in this way, but remember that inverse of e to the power of x is ln x. And when you apply this theorem, this formula in here, let's apply it. So inverse of fx is e to the power of x again, and derivative of f inverse x will be, let's write formula, 1 over f derivative f inverse x equals to, what is f inverse x? Ln x. Let's put it f inverse ln x. And what was the derivative of fx is e to the x. So you will just put derivative ln x instead of x, ln x, e to the power of ln x. 1 over e to the power of ln x. And what is ln x? Ln x is logarithm e to the x, and this part will give you x, 1 over x. Voila. So what we get, inverse of ln x, no, inverse, sorry, derivative of ln x is 1 over x. Easy. Okay, and we have alternative derivation using implicit differentiation. It's easy. You just take derivative of both sides, and then you find dy over dx. We already knew it. I mean, knew the implicit differentiation part. Okay, you can solve all these examples. But one interesting thing in here is modulus function. So, what is interesting here, since modulus x equal to x when x greater than 0, and modulus of x equals to minus x when x less than 0, we'll have nice result. Derivative of ln modulus of x, of course you can write it as d over dx, ln modulus of x equals to 1 over x. Of course x cannot be equal to 0. Okay, this is nice formula that you have to remember from this chapter. What else we have in here? Let's see. Derivatives of a to the u and logarithm a u. We start with the equation a to the x. Okay, so to find the derivative of a to the x, we said that e to the power of ln something will give you that something, because e to the power of ln x was x, yes? So it means what you put in here will be the answer. This is a nice rule that you should remember, and it's really helpful to prove a lot of things. So it means you can write it as ln a to the x, yes? Yes. And we know that ln, let's say 3 squared will be equal to 2 ln 3. It's a nice rule. Also logarithm 5, let's say 10 to the power of 3 will be 3 logarithm 5 from 10. 10 from 5. It means we can write it as e to the x ln e. A, not e. Okay, so, and when you take derivatives of both sides, and let's take derivative of both sides in here. Let me delete it's unnecessary parts. Okay, so derivative of a to the power of x equals to derivative of right part, e to the power of x ln a. And derivative of this function, so e to the power of something will give you the same answer, e to the power of x ln a, but also remember that we have to find derivative of x ln a, d over dx x ln a. And also what we have to do is to put d over dx on the left and everything else on the right. But I think this won't give us an answer because we have to find derivative of a to the x. So let's keep it in here. And e to the power of ln a to the x. Okay, that's nice. This will give us a to the x. And derivative of x ln a is derivative of x ln a plus x derivative of ln a. Yes. And this equals to e to the x times this is ln a. Oh, ln a is function. Ln a is constant, so it means this is 0 times ln a, and it means derivative of e to the x is equal to e to the x times ln a. And that's it. Okay, and of course, when you have e to the power of, let's say, fx, some like functions in here, you have to write again e to the fx times ln a, but times derivative of that function Please, please, please never forget it. For example, let's say you have 5 to the power of x squared minus 3x. You have to find derivative of it. You will write 5 to the power of x squared minus 3x times ln 5 times derivative of x squared minus 3x. Not times ln 5 times 2x minus 3. And here is your answer. It's not difficult. Not that much difficult. Okay. What about logarithm functions? Let's say logarithm, and we know that we can write it as ln x over ln a. Yes. And let's take derivative of both sides. D over dx equals d over dx. Let's use, we don't need quotient rule here because ln a is constant, like number. We can write it as 1 over ln a times d over dx ln x. And what was the derivative of ln x? Of course, 1 over x times 1 over x. And what does that mean? It means derivative of logarithm function equals to 1 over ln a times x. Again, let's say you have not x but a to the, let's say, u function in here. You have to write 1 over ln a times u times du over dx, derivative of that function. Never forget this part, please. Because why we don't write here derivative of x? Because derivative of x is 1, yes? That's why. Actually, there is derivative of x in here, but as it's 1, we don't write it because it's meaningless. Okay, here also inside the box you can see it, and of course a is different than 1. Okay, what else? Okay, these are just this is a nice part actually. Oops. It seems like I won't able to solve problems from related to derivatives of logarithm, logarithmic differentiation, finding derivatives, and logarithmic differentiation with exponentials. Because I want you to choose questions and solve them together. I think it's more, much more efficient way to do. This is second remarkable limit. So we know first remarkable limit. Second remarkable limit could seem a little bit confusing, but it will really be helpful for you to solve a lot of questions. So it is basically limit x goes to 0. When x goes to 0, 1 plus x to the power of 1 over x will always equal to e. Why we need it? Because when you have to find complex limits to the power of something, I mean, you have something fx and to the power of gx, when you're stuck. I mean, you're stuck really. But somehow you will be able to connect it to, convert it to 1 plus something to the power of 1 over that something will always give you e. Then it will be much easier to solve that limit. We'll see a lot of examples. We will solve a lot of examples related to this limit, because actually it's it never come to your mind to solve some questions using this, but we'll solve a lot of questions about it. And you will see that it's not actually that much difficult. Okay, so not tomorrow, but I don't know when I will upload this video, when it will be uploaded actually. On Sunday, I put a poll, I think, in the WhatsApp group, or I think I already did. We'll have Sunday section, we'll have Saturday section and Sunday sections. And on Saturday we'll do exercises from 3.7 related to implicit differentiation, and on Sunday we will dedicate our session to solve derivatives of inverse functions, and mainly not inverse part is easy, but finding derivatives, logarithmic functions, and all this stuff. Okay, so actually I can choose some questions and solve them, but I want us to talk and you to ask questions, and this video, it's already actually 1 hour. I hope you enjoyed it. Bye, see you.